You've done it on every flight. The engines spool up, the plane lurches forward, and you sink back into your seat thinking, this is what keeps us in the air. Those two giant cylinders bolted to the wings, the roar, the vibration through the floor. The logic is so obvious, it feels almost insulting to question. Engines push, wings lift, plane flies. That's the story you were told. That's the story every passenger carries in their chest from the moment they first buckle in. But the truth is far more clever and far stranger than the marketing brochures would ever admit. Here's what the evidence actually shows. An airliner at cruise altitude is not being held up by engine thrust. Not primarily, not even close. At 35,000 feet, the engines are producing roughly enough power to sustain forward motion against drag. That's it, the lift. The force that keeps 400 tons of aluminum, fuel, passengers, and cargo suspended in nothing comes from a relationship so subtle that engineers spent decades arguing about how to describe it correctly. The real pilot of every modern jet isn't the human in the left seat. It's a set of aerodynamic principles that work whether the engines are running or not. And if you've ever sat by the window watching the wing flex upward on a turbulent approach and wondered whether it was supposed to bend that much, you already sensed the answer. You just didn't have the engineering proof. Let's start with what the manuals actually say. The 737's wing is designed to produce lift at airspeeds as low as 130 knots, with the engines at flight idle. Idle. That means the engines are running at barely above ground idle speed, producing almost zero thrust relative to takeoff power. Yet the aircraft remains airborne, descending at a gentle rate of 700 feet per minute. The wing is doing the work. The engines are just keeping the wind moving over the control surfaces. Now consider this. Every glider pilot in the world stays airborne for hours with zero engine power. The same physics apply to your commercial jet. The difference is weight and design, not principle. If you removed both engines from a 737 in cruise, the aircraft would not fall like a stone. It would glide at roughly 2 nautical miles forward for every 1,000 feet of altitude lost. From 35,000 feet, that gives the crew about 70 nautical miles to find somewhere to put it down. That's not falling. That's a controlled descent with a 40-minute window for decision-making. But here's where the engineered deception really begins. The engines aren't the primary lift producers because they never were. They are the speed sustainers. The real lifting mechanism is hiding in plain sight. The shape of the wing itself, calibrated down to tenths of a millimeter on the leading edge. Boeing's aerodynamicists spend years tuning the wing profile to maintain laminar flow over the upper surface at high subsonic speeds. They measure turbulence in micron-thick layers. They adjust the curve by fractions of a percent to delay flow separation by milliseconds. And the reason they obsess over these measurements is that the wing doesn't just lift the plane. It has to lift it efficiently at a single specific speed, Mach 0.785, the standard cruise velocity for the 737 family. That efficiency requires something you've never seen. Hidden inside every 737 wing is a system of movable surfaces, slats on the leading edge, flaps on the trailing edge, ailerons, spoilers, and speed brakes. Each surface resculpts the wing shape on demand, adjusting the camber and chord line to produce the exact amount of lift needed at that instant. During takeoff, the flaps extend to 30 degrees and the slats deploy to create a high-lift, high-drag configuration that lets the plane fly at lower speeds. During cruise, everything retracts for clean, efficient airflow. During landing, the surfaces return to high drag mode. But now the spoilers pop up simultaneously to dump lift and transfer weight onto the landing gear. And those surfaces are not mechanically simple. The 737's flaps are driven by a torque tube system that runs span-wise through the wing, powered by a hydraulic motor that can move the flaps independently if the other motor fails. The slats use a similar arrangement, but they are designed to extend asymmetrically, meaning one side can deploy while the other stays retracted, providing roll control if needed. The system is so robust that even if all hydraulic power is lost, a standby pneumatic system can still drive the leading edge slats to an intermediate position using bleed air from the engines. You've heard that thud during final approach. That thud is the slats locking into position. You've been listening to a mechanical ballet of inch-perfect calibration every time you land. Now, the moment where everything inverts. The engines do something on the ground that most passengers never register. When you're pushing back from the gate, you hear the whine of the auxiliary power unit, the APU, sitting in the tail. That small turbine generator provides electrical power and bleed air to start the main engines. But the APU doesn't just start the engines. It pre-pressurizes the cabin, powers the flight deck displays, and runs the air conditioning, all before the main engines even turn. And here's the part that redefines everything. The APU can keep the plane fully operational on the ground for hours with the main engines shut down. That means your flight doesn't need engine thrust to move. Once the wheel brakes are released, the plane is perfectly capable of taxiing on APU electricity alone, using the nose wheel steering system and the same hydraulic power that drives the main landing gear. The Boeing 777 actually demonstrated this in a famous test flight in 1995, where the crew taxied from the gate to the runway, took off, climbed to 30,000 feet and performed an entire flight profile. All while the APU provided all the electrical and pneumatic power, with the main engines run at reduced thrust for the lift phase. So what does the engine actually do if it's not the thing that keeps you in the air? The engine is the enabler of the wing. The wing cannot extract lift from dead air. It needs forward motion. And forward motion requires thrust to overcome drag. The engine provides that thrust, but critically, it also provides something else: the stabilization force that prevents the aircraft from entering a stall. In a stall, the wing stops producing lift because the airflow separates from the upper surface. The only way to recover is to lower the nose, increase airspeed, and reattach the flow. The engine provides the power to increase airspeed quickly. But even then, the engine is not producing lift. The wing is the organ. The engine is the battery. The engineering world has known this since the early 1950s. The original Boeing 707 test pilots conducted stalls at altitude with all 4 engines at idle, and the aircraft behaved normally. The same recovery procedure applied. The only difference was the rate of airspeed increase during recovery. The wing didn't care whether the power was on or off. It cared about angle of attack, and that single variable. Angle of attack is the only force that truly determines whether you stay airborne. If you've ever looked out the window during a flight and seen the leading edge of the wing pointed slightly upward relative to the horizon, you've seen angle of attack in action. That slight tilt, typically between 2 and 4 degrees in cruise, is what positions the wing to generate lift. The root of the wing is fixed. The angle changes because the aircraft is pitched up slightly relative to the relative wind. The wing doesn't change shape in cruise. The attitude of the entire aircraft changes, and the engines have nothing to do with that attitude. That's the flight control system. Now consider a scenario that happens more often than most passengers realize. The aircraft is on approach at night, rain, low visibility. The autopilot is managing the descent rate. Suddenly, the airspeed drops below the computed threshold. The flight control computer detects the incipient stall and commands a nose-down pitch input automatically. Without any pilot action, the thumb wheels adjust the stabilizer trim, the elevator deflects, and the nose drops. The airspeed increases. The wing reattaches. The aircraft continues the approach as if nothing happened. The engines haven't changed power setting. They are still at idle. The wing did everything. The engine just watched. The passengers never felt a thing. They were busy judging the flight crew's professionalism by the smoothness of the landing. They had no idea the aircraft had just saved itself using only the wing. So why do airlines, pilots, and every pre-flight safety briefing keep telling you that the engines are what keep you in the air? Because the simplified story is easier to sell than the truth. Marketing departments learned decades ago that passengers trust a straightforward narrative. Engines make thrust. Thrust creates lift. Lift equals flight. The alternative: a story about aerodynamic coefficients, Reynolds numbers, boundary layer control, and stall margins. Sounds like a lecture that scares people more than comforts them. So they compress the reality. They tell you the engine is the hero. And in a way, it is. But not for the reason you think. The engine is the hero because it keeps the wing flying long enough to get you across the ocean. But the wing is the real star. The wing never gets the credit. And that imbalance, that structural misrepresentation of aviation's fundamental principle, has created an entire generation of passengers who genuinely believe the plane would fall out of the sky if the engines quit. That belief is false. And the evidence is sitting in every glider field on the planet. Now, here's the escalation. There's a system on every modern jet that actively deceives you into thinking the engines are doing more than they are. It's called the flap maneuvering speed schedule, and it lives inside the flight management computer. During takeoff, the FMC calculates a target speed that ensures the wing will produce lift even if one engine fails. That speed varies with weight, temperature, and altitude. On a hot day in Denver, that speed might be 170 knots, well above the stall speed of the clean wing. The crew is trained to rotate at that calculated speed. They don't rotate earlier. They don't rotate later. They rotate exactly when the computer says the wing will produce enough lift to overcome the aircraft's weight. With the remaining engine at full power. So the next time you hear that rotate call, you'll know exactly what just happened. The wing was given permission to carry the load with or without the second engine. That kind of hidden logic is what turns a boring flight into a demonstration of engineering genius. If you want, that means the engine failure case is already built into the takeoff schedule. The margin is baked in. The wing is designed to guarantee that the single operating engine can accelerate the aircraft to a safe climb speed while the wing carries the load. The second engine is back up for the first. But the wing is the constant. The wing is the primary. The FAA's certification documents for transport category aircraft, Part 25, specify that every airliner must demonstrate a positive rate of climb with one engine inoperative from the moment the gear leaves the ground. The climb gradient must be at least 2.4%. The wing must produce that climb gradient at the calculated speed. Not the engine, the wing. The engine provides the thrust vector. The wing converts it into vertical lift, and the percentage of that conversion, the lift-to-drag ratio, is what determines whether the aircraft actually climbs or just accelerates horizontally. On the 737, the lift-to-drag ratio at takeoff is roughly 15:1. That means for every 15 units of lift generated, 1 unit of drag is created by the wing. The engines only need to overcome that 1 unit of drag to maintain level flight. The other 14 units of lift are entirely free, provided by the wing shape and angle of attack. If you run the math, the engines are supplying less than 7% of the total upward force during cruise. The wing supplies the remaining 93%. That 93% is the part you never see, never touch, and never hear about. It is the hidden system that saves your life when an engine dies mid-air. And it's not hidden in a compartment. It's the entire structure of the aircraft itself. So why doesn't the safety card mention it? Because the safety card has to cover the emergency scenario that passengers can do something about. Evacuation, life vests, oxygen masks. The wing is not something a passenger can interact with in an emergency. You can't deploy the slats from your seat. You can't adjust the angle of attack from the cabin. The only thing you can do is trust that the engineering is already complete. And it is. But the truth is far more clever than any emergency procedure. The next time you board, as you walk past the wing and settle into your seat, pause for 2 seconds. Look out the window. That curved surface, that pale grey metal, that thin leading edge polished by 50,000 hours of subsonic air. That is the most efficient lifting body ever designed. The engines are just loud accessories. The wing is the aircraft. And now you understand why the system behind your safety briefing is not the engines. It never was. Stay with me. Because what you just realized is only the first layer. The second layer is where the engineering gets so strange that even pilots don't fully understand it. And the third layer will change how you hear every announcement for the rest of your flying life. If this opens something for you, tell me in the comments. Which part of this did you already sense but never had the proof for? That's where the real story lives. The wing's supremacy over the engine isn't just a design preference. It's a regulatory requirement written into the DNA of every airliner you've ever flown. The FAA's Part 25, Airworthiness Standards, Paragraph 21, subparagraphs A through D specify that each transport category aircraft must demonstrate a minimum climb gradient with the most critical engine failed at the most critical point in the takeoff sequence. That demonstration isn't theoretical. It's performed physically with a fully loaded test aircraft in front of FAA inspectors before the type certificate is issued. The Boeing 737 MAX certification flights included a series of one-engine inoperative takeoffs at maximum takeoff weight. The test pilots did not feather the dead engine. They let it windmill, meaning the failed engine continued to spin, creating parasitic drag equivalent to roughly 300 pounds of aerodynamic braking force. Even with that additional drag, with a dead engine on one side, the wing still generated enough lift to produce a positive climb gradient of 2.7%, comfortably above the regulatory minimum. The wing carried the plane. The wing, not the surviving engine, was the difference between a rejected takeoff and a successful departure. Now look at what happens when that wing fails. In 2007, a British Airways 777 crashed short of the runway at London Heathrow. The flight data recorder showed that both engines lost thrust simultaneously at an altitude of 700 feet, an event that had never occurred before in the 777 fleet. The crew had fewer than 40 seconds to react. They did not have time to analyze the failure. They did not know that ice crystals in the fuel system had clogged both engine fuel oil heat exchangers. What they knew was that the engines were spooling down, the airspeed was decaying, and the ground was coming up fast. The aircraft did not fall out of the sky. The wing kept flying. The 777's high lift system, powered by the APU-driven generator that remained operational, allowed the flaps to extend to an intermediate position. The spoilers remained retracted. The wing maintained lift at speeds as low as 120 knots, well below the normal approach speed. The crew managed a controlled impact, the cabin remained survivable, and everyone on board walked away. The National Transportation Safety Board's final report explicitly credited the wing's lift retention characteristics as the primary factor in the survivable outcome. That event changed everything in aviation safety culture. It proved that the wing's fail-safe design was not just a theoretical margin. It was an operational reality that could be counted on in the absolute worst case. And it also proved something else. The engine failure did not kill the flight. The approach did not kill the flight. The wing's refusal to stop flying killed nobody. Now, zoom into the microscopic layer. The wing's upper surface is not smooth. It is covered in thousands of tiny vortex generators, small vertical vanes, roughly 1 inch tall, arranged in rows near the leading edge. These vanes do not look aerodynamic. They look like someone glued razor blades onto a smooth surface. But their function is precisely the opposite of what intuition suggests. They intentionally create small vortices in the airflow, micro-tornadoes that energize the boundary layer and delay flow separation. Without them, the wing would stall at a lower angle of attack, reducing the aircraft's safety margin. On the 737, the vortex generators are positioned at approximately 15% chord, the distance from the leading edge to the trailing edge. They are angled at 10 degrees relative to the free stream airflow. Each one generates a vortex that mixes high-energy air from outside the boundary layer with the low-energy air clinging to the wing surface. The result is that the wing can operate at a higher angle of attack before stalling. The margin increases by roughly 2 degrees, which translates to approximately 30% more usable lift in the approach configuration. You've flown past these vortex generators on every single landing. You looked at them and thought they were defects, or dirt, or some kind of damage. They are not. They are precision-stamped aerodynamic control devices that cost roughly $300 each to replace but provide performance gains that would require an entirely new wing design to achieve otherwise. And here's the strangest part. The vortex generators are not optimized for cruise. At Mach 0.785, the vortices they create generate drag. Measurable, real drag that costs fuel. Engineers calculated that removing the vortex generators would improve cruise fuel efficiency by approximately 0.5%. But they keep them on because the safety margin at low-speed approach is worth more than the fuel penalty at cruise. The wing is engineered to prioritize survivability over economy every single time. That tiny vane costing $300 and generating drag at cruise is a physical vote for your survival over the airline's fuel bill. If you want to see the next invisible compromise that engineers hid in plain sight, the one the pilots themselves don't always talk about, subscribe so you don't miss what comes next. And in the comments, write the phrase safety over profit if you'll never look at a wing the same way again. That prioritization is invisible in every passenger-facing metric. No airline advertises, "Our wings are designed to keep you alive after both engines fail." But the vortex generators are the physical manifestation of that invisible commitment. Every time you approach a runway and the flaps extend, those tiny vanes are doing their silent work, guaranteeing that the wing will keep flying long after the pilot has given up on the engines. Now, consider what happens when the pilot does give up on the engines. In the very specific emergency procedure for dual-engine flameout, an event so rare that most pilots never train for it, the flight crew is taught to configure the aircraft for a gliding descent. The checklist commands: maintain best glide speed, extend the ram air turbine if electrical power is lost, monitor hydraulic pressure, and prepare for a forced landing. The critical number in that procedure is not engine restart altitude. It's the best glide speed, typically 160 knots for a clean 737. At that speed, the wing produces a lift-to-drag ratio of approximately 18:1. That means the aircraft travels 18 feet forward for every 1 foot of altitude lost. From 35,000 feet, that gives you a glide range of roughly 100 nautical miles. You have nearly 100 nautical miles to find a runway, a field, a highway, or any surface long enough to accept 400 tons of aluminum at 160 knots. The engines are not consulted for any of this. The wing is the engine now, and it is remarkably good at its job. The manufacturers know this. That's why every pilot manual includes a glide chart, not an engine restart manifesto. The glide chart is the authoritative document for a complete power loss because the wing is the only system that is guaranteed to work in all configurations. The engines are optional. The wing is mandatory. So when you sit down on your next flight and the safety briefing instructs you to locate the nearest exit, the real message they are not saying is this: the exit is the least important part of this aircraft. The wing has already prepared a solution for the scenario you are about to fear. The wing has been preparing since the 1950s, and it will not fail you, even if the engines do. Now, I said there were 3 layers. The first layer, the wing, not the engines, is the primary lift producer. The second layer, the wing is designed to work perfectly with zero engine thrust. The third layer is the one that will break your mental model entirely. The wing does not just produce lift, it produces torque. And that torque is exactly what controls the aircraft when the autopilot disconnects. On the 737, the ailerons are not connected directly to the control yoke. They are connected through a spring-loaded trim system that the flight control computer adjusts 60 times per second. When the pilot turns the yoke, the computer reads the input, calculates the required roll rate, and commands the ailerons to deflect by a specific angle. But the actual rolling moment, the force that bangs the aircraft, comes from the differential lift generated by the left and right wings. The ailerons are just signalers. The wings do the work. In a catastrophic asymmetry scenario, such as a total hydraulic failure in the roll system, the pilot can still control the aircraft using the wing's natural stability. The 737's wing is designed with approximately 3 degrees of dihedral. The wingtips are higher than the wing root when viewed from the front. That angle causes the aircraft to naturally roll back toward wings level whenever a bank angle is introduced. It's called spiral stability. The wing does it without any control input. The engines have nothing to do with it. If the hydraulic system fails completely, the pilot can disconnect the autopilot, trim the aircraft manually using the stabilizer wheel, and fly the approach using only the wing's inherent stability. The engines remain at a fixed thrust setting. The pilot never touches the throttle again. The wing carries the approach, the flare, and the touchdown. It is the only system that remains active from gate to gate. That is the hidden system that saves your life when an engine dies mid-air. It is not a machine. It is not a redundant pump. It is not a switch in the overhead panel. It is the wing, the most elegant, underappreciated piece of engineering on the planet. The wing that you walked past without noticing. The wing that flexed during turbulence, while you wondered if it was breaking. And it is the same wing that will carry you home when everything else has stopped.